Let's solve a challenging differential equation proof step by step. We'll start with the given equation and transform it to prove our target equation. Let's start by converting our logarithmic equation to exponential form, taking e to the power of both sides. We get y equals e raised to m times inverse cosine of x. Now comes the key part. We need to differentiate both sides with respect to x. Using the chain rule and remembering that the derivative of inverse cosine is negative 1 over square root of 1 minus x squared, we get y 1 equals e raised to m inverse cosine x times m times negative 1 over square root of 1 minus x squared. Let's simplify this equation. Multiply both sides by square root of 1 minus x squared to eliminate the denominator. This gives a square root of 1 minus x squared times y1 equals negative my. Now, let's square both sides of this equation. This gives us 1 minus x squared times y1 squared equals m squared y squared. Here's where it gets interesting. We need to differentiate this equation again. Using the product rule on the left side and the chain rule on the right side, we get 1 minus x squared times 2, y1, y2 minus 2x, y1 squared equals 2m squared, y1. Let's simplify this equation. Factor out y1 from both sides, and divide everything by 2. This gives us 1 minus x squared times y2 minus x, y1 equals m squared y. Finally, we can rearrange this to get our target equation. 1 minus x squared times y2 minus x, y1 minus m squared, y equals 0. And there we have it. We've proven what we needed to prove. This proof demonstrates the power of calculus in solving complex differential equations. We use differentiation, the chain rule, and algebraic manipulation to transform our initial equation into the required form.